Okay, all right. So welcome to our webinar about leak detection on large diameter pipelines with guests from the company F.A.S.T and AP Sensing. My name is Elaine Schung and I'm advisor in the GIZ project Water and Wastewater Companies for Climate Mitigation. And I will moderate today's session for the next 90 minutes. And well, thanks for joining us. So in order to understand who's participating in this webinar, I strongly encourage you to shortly introduce yourself in the chat function, simply by stating your name and the project or the company you're working for. I will post an example just here so you know how to proceed. So today you will hear a short introduction to leak detection and large diameter pipelines by Stefan Siemdorf, where he will explain some of the occurring issues and challenges, and he will also give an overview of known leak detection methods. Afterwards, we have our guest Edmund Riele from the company F.A.S.T, who will talk about leak detection with the hydrophone inspection device PipeMic XL, XXL. And last but not least, we will have Mr. Pohl and Diode, who will explain permanent leak monitoring by means of distributed acoustic sensing and optical fiber cables. All right, so this webinar is brought short COP, which focuses in general on resource efficient water management. And within this community, you can share experiences, but we can also develop solutions in the area of water loss reduction and energy efficiency together. So if you're not a member yet, feel free to contact Mr. Stefan Siemdorf, who will also post his email address in the chat function, and then you can become a member of this community of practice. I can also post it directly in the chat. So we have currently more than 200 members around the world. So the idea of the COP is to actually connect, on the one hand, GIZ colleagues around the world, but also partners and external companies. So we have a knowledge exchange. So if you feel like you have an input that you would like to share within this community, feel free to reach out to either Stefan Siemdorf or me. In the community of practice, we currently focus on the following 3 topics. So the main topics are management of commercial losses, with the subtopics unauthorized consumption, customer meter inaccuracies, and data handling errors. Then we have the topic water loss management, with the subtopics active leakage control, speed and quality of repairs, pressure management, and asset management. And then between management of commercial losses and water loss management, we have the common subtopic non-revenue water, concept, calculation, and indicators. The third topic is energy efficiency in water utilities, with the subtopic organization for energy efficiency, pump efficiency, energy efficient wastewater treatment, energy recovery and generation, and end users water and energy efficiency. And then we have transversal teams. So these are all topics that occur in all of the 3 main topics that we have identified. So the structure that you see here, or the topical landscape, is not a carved in stone. So depending on the demand of the community of practice, the topics and subtopics can be changed, reclassified, broadened, or eliminated over time. Okay, and this slide gives you an idea of what we did in this last year, 2020. So we had several webinars that we organized, among others with the Inter-American Development Bank on innovative technologies in non-water reduction, and also improving energy efficiency in water utilities with innovation. We also have studies on technologies for localization of illegal connections. For example, we already had leak detection large diameter pipelines. We had meetings to revise the structure of the COP, and so on and so forth. I'm not going to go into detail, but we've already organized a few webinars on different topics concerning the three main topics that I just presented. All right. I think something quite interesting is that we also work on publications together with the COP members who are interested. So we had one study where two publications came out of it. So one publication was the comparison of technologies for location of illegal drinking water connections available in Spanish and English. You can directly click in the presentation to access the links. Then the second publication is the detection of illegal drinking water installation with the use of water hammers, also available in Spanish and English. And we're currently in the process of finalizing the latest document called Smart Water Management, Digital Applications to Reduce Non-Revenue Water and Increase the Energy Efficiency of Water Utilities in Emerging Markets and Developing Economies. So this study is close to be finished. I expect it to be published either next week or the week after that, and we will inform you. We have a planned publication for next year, which will focus on the comparison of technologies for detection and location of water leaks. Okay, and this is it from my side. Stefan, I hand over to you.
Thank you very much, Elaine. Yeah, just directly related to that publication we are planning for the next year about leak detection. We have our webinar today, and I will give a very, very short introduction. The reason why we are coming to you for the second time with this interesting topic is that we've seen that it is a niche where technology has advanced really a lot in the last 10 years and can be really, really helpful to bring down non-revenue water. At least here in Peru, for instance, most utilities never ever had a look for leaks in large diameter pipelines. And the reason is because they don't have the technology. So if you have, like, say, 10 or 15% of your pipelines where you just never ever detect a leak, even if the pipelines already are 35 years or more in service, that's a real problem. And we can solve it now. Can you switch to the next slide, Elaine, please?
I'm happy to do so, but you can also take over the presentation if you want to.
Yeah, okay, for 2 slides. Okay, I take over. So, okay, what are the specific problems? Why are so many problems to finding leaks, especially in large diameter pipelines? Well, the first one is, of course, okay, wait, up. The diameter. The bigger is the larger is the diameter, the less the sound propagates or has a very low travel distance of the sound of the leak in the pipelines. Yeah. So they can often not be detected with the same methods used in distribution networks. For instance, here you can see how it propagates in different materials in different diameters. It's very clear. The higher is the diameter, the less is the travel distance. Another factor is you have normally much fewer access points, but often you need a lot of access points to use several methods. Yeah. So as you have much fewer access points, let's say often there are hundreds of meters with Austen and many methods rely on that, that's a really problem. Then often these kind of pipelines are deeper. It makes also much more difficult to find leaks in these kind of pipelines. And finally, in these really, really big pipelines, it's at least inconvenient, if not impossible, to interrupt the service. So taking that all together, you normally will find that standard leak detection methods do not work in this kind of pipelines, and you need other methods. So now there are a lot of methodologies. Maybe you remember the last time in April when we had a webinar on this topic with two different methods. Yeah, I already gave an overview, so I will not repeat that overview, but make it much more shorter. So you can use, for instance, hydrophone copulators. That's a good option if it's possible to gain at least some access points to the water column in that very pipes. Then you have pushed hydrophones. I don't want to spoiler you, but Edmund Rilo will speak about it, about his PipeMic XXL. Then you have also tethered microphones, like the famous Sahara system, yeah, which travels to the pipes large distances propelled by a parachute. The problem with this method is it's really not very cheap. Let's say it's the most expensive option of all. Then you have floating hydrophones. We had a very interesting presentation in our last webinar in April about that by Aganova from Spain. So it's somewhat cheaper, and it consists about a hydrophone that is like a ball that's floating through the pipe and records leak sounds. And then finishing the acoustic methods, yeah, we have the distributed acoustic sensing. That's a very different approach. It's the only one that does not use hydrophones. And it is a little bit like having a lot of microphones around the pipe, but I'm also don't want to spoiler you because Alex de Jode and Clemens Pohl will speak about that today. Then you have some methods that are not non-acoustic, like drone thermal imaging. That's an option that's used widespread for hot water pipelines, and rarely, but sometimes, depending on local conditions, can also be an option to find large diameter pipelines. Then another option that is using also cables is the distributed thermal sensing. That we had a presentation about that in April by GTC Sol Expert, and for sure it will be referred again by Mr. Pohl and Mr. de Jode today a little bit, I think. An interesting option is for not so large diameter pipelines and not so long pipes is the use of tracer gas, injecting bubbles into the water stream that can be traced. We are going to send you with the minutes a link to a very interesting webinar held by our presenter from today, Edmund Riele. He made a webinar about that for the IWA on that. So we will include the link to that very interesting webinar in our minutes that we are sending you today. Speaking of that, I think many people still are connecting. So if you want to receive the presentation, the record and the minutes, it's really necessary that you would like, if you would write down your name, your institution, and your email in the chat, so you can receive all those materials. Then somewhat curious is that sniffer dogs smelling chlorine can also be used sometimes. Of course, that works not with, but you can find a lot of videos, especially from Great Britain, with really cute sniffer dogs on YouTube, and it seems like it's an option that is a little bit increasing. Yeah, interesting option. Also, then there's the option to use this new system. Everybody's speaking about it with satellites. We also have some links about to webinars for that, so it's a little bit more easy to understand it if you look the webinars. So then we have the moisture management cables. Yeah, that is an option we still do not know much about because we are still finishing our study of techniques for leak detection. So we are trying to include the study still in the next year. Yeah. And the last but not least message, it's a method that works a little bit like a correlator, but detects leak in the very moment the pipe is bursting. So it can be used only as a monitoring system. It is not as precise as the system we are going to see in our second presentation today. That's also a monitoring system, but it's a widespread used system, the negative pressure wave method. But that's the overview. And with that, Elaine,
Yes.
sorry, I take over, please, again.
Yes, thank you, Stefan, for the short overview. Yeah, so now I would like to hand over to our first presenter, Edmund Riele, International Sales Manager at F.A.S.T, and he will talk about microphone. So, Mr. Riele, I'm handing over to you. Please upload your presentation.
Yes, thank you, Mrs. Cheng. I will share my screen. So, hello everyone. Thank you for the opportunity to speak here in this nice format. So, thanks to the GIZ for this very professional approach and the good overview Mr. Siemendorf just did about the different methods and technologies used for large diameter pipelines. I also have at the end of my slides a little overview, but not that many as Mr. Siemendorf mentioned. So the dogs, for example, a very unique technology. And I heard about that first time when I visited Australia, Perth, and the people very enthusiastic about it. Yeah, I want to give you now the overview and introduction about the PipeMic. So it's the push-pull hydrophone to push inside large diameter pipelines. But first of that, I want to give you an overview about the whole portfolio the company of F.A.S.T is offering. So actually, the company is offering the full range of leak detection equipment. You see here the different steps. We call it the pyramid of success. Just a second, I put my pointer. So this is the pyramid of success, where you have on the bottom line always the monitoring, so that you know exactly in which zones you lose how much water, and further of that you can coordinate your leak detection activities in the different zones. Of course, you usually start where you lose most of your water. If the pipes are unknown, if you don't know where they are, you need to do pipe searching prior of pre-locating, and correlation is, let's say, a step also doing the pinpointing, that meaning exactly positioning the leakage. But because it's very sophisticated and also one of the oldest technologies in this field, we made it special category. And also my company, F.A.S.T, is actually was developed from that technology. So correlation and correlators were the first thing built by the company F.A.S.T. Okay, then about the unique PipeMic series we developed. Let's say it was actually myself. The first job in F.A.S.T from myself was developing the PipeMic, and I started with let's say house connection and small diameter pipeline hydrophone push-pull rod, the PipeMic M. And during exhibitions in F.A.S.T and Water Berlin, we had many customers saying, okay, we have problems in large diameter pipelines. Can't you do just a bigger rod, more stiff, that it can be pushed longer distances? And that's the reason, and yeah, why we came up after I think half a year. It was not a big step anymore to develop a little bit bigger diameter hydrophone. We now have the PipeMic XL and XXL. And this has a 9mm push rod, and we can equip that with up to 300 meters of the push rod. Let's say 300 meters is already a very tough job to push. So in the end, I was personally able to push in a DN80 pipe, which is quite small. So as more space the cable has, as less distance you can push it. But as more friction you also have on the cable. So I was able to push 270 meters manually by manpower, but that was already a quite tough job. We also, the latest development, it's only 1.5 or 1 year old, is the PipeMic Flex. We encountered many issues, especially in the house connection side, that you have often 90-degree bends going into the wall and then doing some more bends, and you never know where it goes. So to overcome this problem, the PipeMic M was not able to turn in these pipes when the diameter was smaller than DN50. I developed the PipeMic Flex, which has a much more flexible push rod and a much more flexible head. And with this, I will show later a small video. You can take multiple 90-degree bends in quite small diameters down to DN20 or even DN15, depending on the construction and the angle of the bend. Okay, how does this work? Very important, of course, is the tip. So we have a kind of a hydrophone, which is actually not a real hydrophone. Speaking of Bentos or other manufacturers who have this piezo ceramics molded in a rubber coating. So it's actually a real condenser microphone, which is inside a waterproof housing. And this will very sensitive record and pick up noises from inside the pipeline. So the biggest benefit of this technology is that you don't have any environmental noises, you don't have any disturbing noises for example, correlation or with the ground microphone for the pinpointing. So this is a very big benefit of this. And of course, once you are in the pipeline, you will find almost all kind of leaks. So we even found, like we call it, sweating gaskets, where you only have like dripping water coming out of the pipe, and we're able to even detect them with the PipeMic. So it's very sensitive and a very good technology. So once you're inside the pipe and you're able to push a distance, you are absolute sure that you will find all the leaks on this section where you're able to push it. The good thing with the PipeMic is also that you're able to trace the head and the cable. So you see here in this nice illustration, the green and red check here on the PipeMic. You can connect a cable locator, and the cable locator will send out a signal. So usually we use 33 kilohertz, but you can also use other frequencies if your cable and pipe locator is able to do that. And it will emit then the magnetic field to the surface, and you can detect that and really tell exactly on that location the tip is at the moment. And usually you leave the tip on the position where you found the loudest noise with the PipeMic. Okay, so here is a little bit better and nicer overview with some bullet points. So the PipeMic key benefits is really that we have a push-pull rod with different stiffnesses. What I told you in the beginning, we have now the 3 different types: the Flex, the M for let's say distribution pipelines up to DN 100, 150, the XL for up to DN 500, 600. You need to consider as larger the diameter of the pipe, as more space the cable has, as more problem you can encounter inside the pipeline, especially when the tip hits an obstacle and the cable curls up. So this is still an issue. But yeah, you are able to push quite a long distance with the XL and the 9mm push rod. As I already mentioned, we have the microphone with integrated surge coil, the PIC, as many people call it, to connect to the cable and pipe locator. And of course, very important, especially here in Germany, is the hygienic part. So we have integrated disinfection. You see here this small container with the blue lid on the water lock, and this will continuously push the rod through a disinfection liquid, which is then not absolutely, but it's mainly hygienic to be able to push inside freshwater pipelines. Then we have the famous water lock, of course. We need to keep the water pressure inside the pipeline, because without pressure you don't have any noise. This is very important. And the water locks we have are designed for up to 16 bars for the Flex and M, and up to 10 bars for the XL. As larger the diameter, as more complicated the sealing is, as more area the water or the pressure has to work on it. Therefore, we have to reduce the maximum pressure for the XL. Then we have also a meter counter. So if you don't possess a cable or pipe locator, you can also tell exactly how many meters of push rod you pushed already inside. And if you know the run of the pipe, you can just measure it with a measuring wheel or a scale on the street or wherever you are. And the signal is transmitted from this small electronic box inside the PipeMic via Bluetooth on either a speaker or a headphone, and is very clearly audible. We will show that in a video in a second. And yes, I already mentioned 2 times now, but again, so the wire and tip location can be done with any standard cable and pipe locator. So we are not limited to one brand or one frequency. You can use any type. Okay, here some more illustration how that works with the line location. The push rod has copper wires built inside, and this you can apply the magnetic signal, electromagnetic signal from the pipe locator, and you can detect that on the surface. And the tip, or the pick on the tip, is then 90-degree turned. So as you can see, the magnetic field here is in these circles and here in that circles. So you also need to turn the receiver unit in order to locate the tip. But when you find the tip, you're absolutely sure you're right on the spot of the leakage, and there is no black or white. There's only black or white, yes or no. So there is no gray area like with the geophone. You sometimes pick up a noise and you cannot really distinguish if it's now a leak noise or maybe an environmental noise. With this technology, you're absolutely sure you're on the spot. Okay, the main issue of the PipeMic is always the insertion of it. We have a lot of inventive customers who one of them also gave us the idea of this insertion tool, guiding tool, insertion guide we call it. It's basically a simple PE pipe with an opening, you can see here on the right, into one direction. So it's guiding the tip and the cable in one direction. Therefore, you can also, when you have an insertion position, go with the flow and against the flow. So you're not limited as with the tethered devices with the parachute. You can also push against the flow. So basically you can, with one hot tab or one insertion position, cover a distance of about 400 to 500 meters, depending on how far you can push it manually by your hand. Okay, we have a 1/2 inch or 1.5 inch thread to be connected to, usually we use these drilling saddles as shown in this picture. This one is from Havle, a German manufacturer. You can basically use any type of drilling saddle. You need to make sure that you have at least a bore hole of 32 millimeters for the XL and 25 millimeters for the PipeMic M. Yes, we have a lot of success actually with this device, especially worldwide. I just highlight some cases here. One in Russia who even wrote us a recommendation letter from Mosvodo Canal, and yeah, they were able, even under the harshest conditions in minus 30 degrees, to really precisely locate the leakages in their pipelines, and they were really happy. And many other stories around the world, especially also in South America. A young colleague of mine started to promote the PipeMic 2 years ago in South America, and it's also starting to pick up some interest here. Okay, last but not least, I want to show you some small videos with some audio, so that you also get an impression about how the PipeMic sounds. So Elaine, I will just go for the video. Okay, so that was actually in Saarbrücken, a case where that was the first prototype I built, and we inserted it in here in a 400 millimeter ductile pipeline, which was a quite delicate place, marketplace, next to the castle in Saarbrücken, and we were able to locate the position of the leak exactly on the spot. Another video I want to share is from the PipeMic Flex. Just a second. Include system audio again. Where is it? Here. Okay. So this is actually from the YouTube channel.
Value later on when you pushed it inside. Okay, what I wanted to demonstrate to you here in the dry is I have here the 90-degree bended pipe section, which is a TN32, and I have connected here the GECA coupler. I will just put it onto this table and demonstrate to you how easily you can really push this flexible head around the different angles and bends. Okay, I connected. Push it inside. You see already my hand is going very smooth. I don't need a lot of force. Now you see here, film it on the third curve. I am now here. If you feel some resistance, go back, and then with a little force you go further again, and you see it coming out at the far end.
Okay, and the last video is from the PipeMic itself, with some tone about the leak, where you can directly experience how it sounds. So, just a second, I will share the next video. Yep, here we are. So this is still the installation. I skipped this part to only show you how the leak sounds and how precisely you can actually locate the leak. It's like a surgery tool from doctors to locate some injuries or so in your blood channels or so. What you hear there is the normal push sound of the hydrophone, and then when you approach the leak, you really have this very loud tone or leak noise. And you see here the hand is only moving like a few centimeters, and then right on the spot you have the maximum intensity, and therefore you can locate it quite accurate. Okay, that's all from my part. I will hand over to Elaine, and yes.
Yes, thank you, Edmund, for the presentation. Very interesting. And we have received one question so far. So I will just read it out loud. So one question from a practitioner. So from experience in a project in Syria with diameters up to 200 millimeters, we detected that the biggest losses are mostly on the house connections, as they are often not well done and prone to bad building quality. So in general, is it possible to make a statement on how important leakage on larger diameter pipes really is?
Really are. Yes, indeed, as Mr. Siemendorf introduced in the beginning, the largest diameters are the pipes which are often left aside, but which have a contribution towards the NRW on a quite big scale, I would say. But as they are some of the most difficult to detect and the most costly to detect as well, usually it's easier to start, especially with the house connections. So therefore, the contribution towards NRW of the large diameter pipelines is significant. But often, it's like too complicated, I would say, or it was. Now there are more technologies evolving and coming up. So in that sense, I think it becomes more efficient to also detect the leaks on large diameter pipelines. I know, for example, one case here in Baden-Württemberg, in the south of Germany. They have the Alp tunnel where they pump the water from the Lake Constantia, which is the biggest freshwater lake in Germany, towards the city of Stuttgart. So it goes through a whole mountain, and they lost a huge amount of water. So, and they actually, during the time I was still a student, they told me they inserted the Sahara and the smart ball, and they couldn't locate it. In the end, it was a diver going, because this is a huge tunnel with about 2.5 meters diameter. And Mr. Messerschmidt, who is also investigating the caves in the Donau Valley, he, with his robotic, went through the tunnel. So a very impressive job he did there, because you could not locate it with other technologies.
Thank you for answering the question. I hope that that was satisfactory for the person who asked the question. Then we have another question regarding trainings. So do you also offer trainings?
Yes, absolutely. Yeah, we have our own training base in our headquarters in the south of Germany, which is close to the city of Heilbronn. And yeah, therefore we can give hand-on training. Also, what we currently during Corona do, most of my job is virtual presentation, webinars, and so on. So we're very experienced with that already. And of course, our goal is to receive customers and clients in the future personally again, to give them really hands-on training on the equipment, with the equipment in the field, which is usually the best method to train on.
Yeah, and thank you again for also joining us today to give this presentation. Very valuable. Stefan Ziemdorf raised his hand. You can unmute yourself if you want to.
Yeah, I have two questions. One is, of course, I already know the answer, but I know everybody wants the cost of the equipment, of the devices. And another one is, well, I think it's very easy to understand this method. I think all the complication is inserting the PipeMic. So which fittings that are normally exists in these large diameter pipelines can be used for that?
Mm-hmm.
And how do you gain access? You already mentioned it a little bit. Would be nice if you can send maybe some additional material so we can include it in the additional materials for the sessions. But especially I want to know, I know I was recommended to make an inspection of large diameter pipelines every 2 or 3 years. So if you do not have access and you drill the access, isn't it that you, if you already gained access, that you just let the new fitting there for the next inspection? Can you give a recommendation on that also?
Yes. First of all, the first question about the price is roughly about for 150 meters or 100 meter XL, about 4,000 euros, 4,500. The XXL with 300 meters then costs about 7,000 euros. So this is for the basic costs of it. And the second question about the and the different access spots. I have seen many very innovative approaches, or let's say not innovative, but people getting very many ideas how to insert it. The usual position or spots, access spots, is valves or washouts on the large diameters. What you can use to insert it. We used it in Dubai on the air valves to insert it. Also in China, the air valve was easy to dismantle and push it inside. Then in India, we mainly use like solar, not solar, but they with the, is it soldering? No, soldering is with the hand. When you put the metal on the metal pipe and they welded, oh, I got the right word. They welded some nozzles on top, and then they drilled it and left the nozzle on it. So with a small ball valve to shut it once it's drilled. So there is a lot of different accesses. Last but not least is this drilling saddles, which is common for house connections, at least here in Germany. We use these small gate valves for the house connections, where you also have the spindle, which is then the operating spindle for the valve on the surface. And those are the typically the insertion position and the access spot where you can insert it. And I think there was a third question. I excuse myself. I think I forgot. Can you maybe remind?
If you let it installed the recently gained access for the next inspection.
Of course, that's perfect. As more access you have to the pipe, and if you leave them still operatable, if you come again in 2 years or whenever you have experienced the next leakage, you will be able to operate it on that position. It's totally no harm to leave it like this.
Okay, before we move over to our next presenters, we have 2 remaining questions. So one is, do you have estimates of how many meters of leak detection one person can do in a day in a network?
This is a good question. It's always a question back about how well is the insertion positions prepared already. So if you need to do everything on your own, that means you're the plumber of the water company, so you also need to dismantle the air valve or prepare the washout for the insertion. This will take the longest time, but if you have someone doing this and you only are the guy who is operating and pushing the PipeMic, then I would say you can easily push like 1 kilometer a day or even more. But of course, the preparation is the longest period it takes.
Is there a follow-up question by the person who asked this? Otherwise, I will move on to the next question, or you can. Okay, all right, so that was satisfactory. Then the last question. So what is the maximum size of pipes which can be inspected, and is the technology problematic in regards of spreading sediments that can be present in old pipes?
The maximum size of the PipeMic XL, I would say, still a good size is 650, 700 mm. More than that is, as already mentioned, if you have obstacles inside, mainly joints, where the different pipe sections were put together, and the tip hits this obstacle and stuck there, the cable in the end will curl up, maybe even make a knot, and then you won't be able to retrieve it anymore. So therefore, it's quite delicate job by the guy who is pushing it inside to feel these resistances, especially as larger the pipe diameter is, as more problems you can encounter. Therefore, my recommendation is 700 millimeters maximum, not more. And of course, yes, with the PipeMic, it moves on the bottom, so it's not like floating, and therefore you will steer up sediments when they are there. But if you have sediments, then the pipe was anyway due to flushing. Maybe it's even a good way to do it on the same job, detecting the leak and flushing the pipe, so that you have no issues with brown water or turbid water.
Thank you for answering the question. This is really the last question, but I feel like you already addressed this during your presentation. So how do you make sure not to contaminate drinking water pipes with the mic?
We have the disinfection container, and we use like, I think it's 5% solution of hydrogen peroxide, which is killing viruses and bacteria. And as you push the rod inside, it gets dragged through the disinfection liquid, and a small film is covering the rod, and then it's hygienic to use. And of course, before you insert it, you also have a spray bottle. You generously spray the head so that it can really have the time to react if there is any contamination or bacteria on it. Of course, you should not use it in sewage pipelines and next shop in a freshwater pipeline. I have some customers actually wanted to do that, and I mean, it's out of question. Once it was in a wastewater line, you should not use it in freshwater anymore.
Okay, yeah, I thought this was common sense, but thank you so much for mentioning this again, and thank you for the questions from the participants. So thank you, Henrine from F.A.S.T.
My pleasure.
And we will now hear our next presenters. So we have from AP Sensing, Mr. Clemens Pohl, Managing Director of AP Sensing. And we have Dr. De Jode, Head of Pipelines and Terminals Business Unit. So I kindly ask you to share your screen or share the presentation, and I'm really excited to hear your input.
Thank you very much. Alex, I guess you will share the presentation. So first of all, thanks to Ms. Zhang and Mr. Zimmendorf for the opportunity speaking to you, and thanks for your interest. Also, the first presentation was very interesting to me. So hopefully we can share something new. We are talking about fiber optic sensing, and let me share. Okay, Alex, would you approve my request for control? Oops. Okay. See that. So give us please a second. Just allow. Okay. Yeah. Okay. Great. So quickly about AP sensing, then we will talk about the application distributed acoustic sensing and distributed temperature sensing in large diameter, but also sewage pipelines, and share a bit more about the technology, some machine learning algorithms and other technology, looking at visualization and, if you like, some references. So quickly, we are actually located in Germany, but we originate out of Hewlett-Packard, which some of you may know. HP started as a test and measurement company, and in 1939 set up a first site outside the US in Germany, where we are located. And in 1999, the measurement business was spun off, and in 2007, AP Sensing was formed to focus on the fiber optic sensing market. Well, we see ourselves as a leading provider for that market. I will just skip this maybe. We are addressing multiple markets with the technology. We go into applications like fire detection. So, for example, we are monitoring the Eurotunnel and are activating the suppression systems in case there's a fire on the train. We also observe high voltage power cables, whether they are from an offshore substation or a wind farm coming to onshore, or even transmission lines along the country. Pipeline that can be water pipelines, but also gas, oil, other pipelines. We go into liquefied natural gas tanks, doing leak detection there, but also observing and controlling heating processes. Oil and gas reservoir monitoring, but also into geothermal and geotechnical applications such as dam and dike leak detections, perimeter monitoring, and tracking rails. So quite a lot of different applications, and the base for all of this is basically a lot of technology. So we see ourselves as a technology company. We have quite a lot of investments going into this, and basically it is about all about fiber optic sensing And I will just skip to the next slide. We are globally present and have our offices mainly with technical support and technical sales. The headquarter is here in the southern part of Germany, actually very close to the company of F.A.S.T. And yeah, but we are obviously closer to the markets. And yeah, now we come more to the technology. Quickly, what are we doing? So we have these so-called fiber optic sensing devices, these gray instruments on the left. And these boxes are basically connected to an optical fiber. So I guess most of you know what an optical fiber is. They're typically used for telecommunication. So they are right now probably quite used for transmitting this video conference around the world. And there the data is basically just transmitted. What we do is we also send a light pulse into the same fibers, and we get some back reflections. And those back reflections we can analyze and thereby read the temperature along the optical fiber. So in the first device, what we call the DTS, distributed temperature sensing device, we measure the temperature for every meter. So assuming you have 50 kilometer, then we have 50,000 temperature points. And we get this continuously. So for example, every minute we have an accurate reading, and thereby if there's any change in temperature, we can detect this along the entire distance. And very similar for the distributed acoustic sensing, we are basically listening for vibrations along the optical fiber. So if there's somebody, so it's kind of a hydrophone, but not one, but more like 50,000 microphones. And these is using the glass property, and as vibrations hit the fiber, it actually changes the length very slightly of the fiber, and we are able to read out this change. And thereby you can imagine it's almost like playing an MP3 file for every meter along the fiber. Here we can see, for example, if somebody is walking close to the fiber, if somebody is digging, if there's a leakage, if there's an explosion, if there's a train, or whatever. One thing, it's not for recording voices. So if I would speak to the fiber, the acoustic energy of my voice is not enough to really have an impact of the fiber. But if I'm walking, for example, close to the fiber, that is giving these vibrations which we can detect and kind of listen to. So that's kind of those two core technologies. And now you probably understand why we are able to address so many different markets. At the end, it's just physical measurements we do, and now we put some intelligence on top so that we can either detect a fire or a leakage. For example, in a gas pipeline, it becomes very cold. Acoustically, as just presented by the F.A.S.T. company, if there's an acoustic event, we can hear the sound, but also, for example, a negative pressure wave originating when the burst happens. And yeah, I guess with a few more slides to more explain the basic technology. So again, we have this device. That device can be somehow connected to a monitor or a control center, so that we typically have permanent installations. The fiber is our sensor. It's completely passive. There's nothing in that fiber. It's just a fiber as you would use to transmit data. We send a laser pulse into this fiber. With every molecule along the fiber is a little bit our sensor. So that sends the back reflections. And if the properties change in this glass molecule, we are detecting it. In this example, we have a temperature trace, and at one location, I think it's down at somewhere around 30 kilometer, there's a hotspot happening, and we immediately detect such a hotspot. Now, the beauty of this technology is that it's permanent. It's continuously monitoring the entire distance. So it's over time and distance, and there's no other technology out there which can permanently see any changes over distance and time, whether it's for temperature or acoustic. So just to illustrate the benefit of this technology, so on the very lower part here, you see a temperature trace. So this is actually an example of a normal installation where you have, if you go underneath the street, if you are at a manhole or wherever, you always have some different temperatures. So if you now, for example, in this case, there's a heating process taking place, you can see the changes for every meter, and you can immediately detect those hot spots or cold spots, and it's quite easy to analyze. What we do now, on top of this, we have algorithms to detect very small changes and basically give alarm of whether there's something abnormal happening or a leakage happening. On the next slide, I want to just explain how the acoustic sensor works. So here, because it's so nice to see and easy to understand, there's actually a track from Berlin going to Dresden. It's a train track, and there's a fiber running next to that train track. Now, if there's low energy, it's basically colored as blue. If there's a lot of, it's red. And here, it's directly taking the energy from the fiber. And if I play now here, start, you would see these two trains running on the track. Obviously, there's two tracks, so there's no crash happening. And we can now in real time see where the trains are and how they are progressing. We use this, for example, to not only know where the train is, but also how fast it is, if there's any defect on the wheels, if there's a defect on the train track. So quite a lot of things we can get by the signature. Maybe quickly about the signature, we get the frequencies from 0 hertz to up to 2000 hertz. So it's not a high frequency sensor. Yeah, I guess I would hand over to Alex with the next slide. So probably a stop control. Then Alex, you should have control now. If you would unmute Alex and continue. And okay. Maybe even show your video if possible. Great.
All right. Okay. The distributed acoustic sensing can detect leaks. Can detect leaks by listening to the noise of the leak. Can also see changes in temperature. So this name distributed acoustic sensing is not quite correct because you can see changes in temperature. So distributed temperature gradient sensing. And we can also detect the negative pressure waves generated by the onset of the leak using DAS. DTS is a bit different. We are looking at the thermal signature of a leak. So if you have a hot liquid like a sewage, you were able to detect the leak by monitoring the ground temperature around the pipeline, the effect on the environment that's caused by the leak. I had this table here inspired from API 1175 for pipeline management, leak detection management systems, and where it's classified the types of leak detection in continuous in real time and non-continuous, meaning inspections. Aero surveillance, for instance, inline inspection, as was shown before. And with DAS and DTS, you can have an external or internal, if the cable is inside the pipe, monitoring of the pipe. So we also have the ability to detect leaks with reference to the size of the leak. So with SCADA monitoring, just looking at pressures and flows, you are not able to detect small leaks and SIP leaks, and you are possibly detecting medium leaks and pipeline rupture. With CPM, which is computational pipeline monitoring, real-time transient models, flow balance, and statistical flow balance, you are able to detect possibly small leaks and medium and large leaks. The problem with the challenge, let's say, with large diameter pipeline is that even the small leak rates of 1 to 3% are very large leak events for because of the flow rates that we're talking about. So all these methods, they rely on flow meter accuracy and repeatability, and you are ending up detecting, possibly detecting small leaks, but detecting medium leaks is a bit too late, let's say for 1.5. Leak detection in large diameter pipelines are that the large diameter flow meters are expensive and also have calibration issues. You have you bought up your flow meter, you calibrate it, and over a period of time, a few years later, it's difficult to calibrate. What happens sometimes, you have multiple pumps, and this flow metering is spread over smaller pipes. But what happens is you have to do the flow or mass balance between 3 flow meters on one side and 3 flow meters on the other side. So you have the compound metering errors between 6-8 meters, right? And again, it increases the size or the minimum detectable leak. Another issue is when you have your network, your big diameter pipe, and a new connection is made, and some of these connections can be quite substantial, and so your mass balance, your flow balance is totally destroyed because you have unmetered. Okay, it is metered, but not in real time. So you are not doing leak detection in real time anymore. And also because of the price and the size of the flow meters in very long pipeline networks or long trunk lines, the flow meters are quite far apart. They are hundreds of kilometers apart. So the location starts to be a big issue as well. Location is important, and I have a few examples here. Another, this is a spigot belt situation where you have many joints on a pipeline, and these pipes, they can be as big as 4 meter diameters, and you can see the leak at the joint here. And this leak is an incredible video in Manaus, in Brazil, and it was caused by a leak on the joint, and the joint in the leak, the pipeline lost support, and it broke here. You can see the fracture on the ductile iron pipe, and because it was on a bend, it was going down. This pipe is on top of that hill here, on the curve, and it putting stress on this pipe here now. Another challenge for large diameter pipes is detecting rebar failures. What to on pre-stressed concrete cylinder pipes, and you can see here there is some exposure of the rebars, right? And this when they fail, the pipeline starts a leak, of course, but there's a big time difference between starting the leak and the leak developing. So we could there are some clients already making significant economies by repairing these pipelines before it leaks. Here's it's again a very nice film. I put some slides here, and you can see on this on the bottom corner here the pipeline, the leak here, the hole here, and the damage that it made on the water reservoir, right? So this is a massive damage, liability caused by a leak that perhaps it could have been prevented if there was it was monitored by fiber optic. Another challenge for leak detection is in water pipelines is the detection and location of multiple and simultaneously slow-growing leaks. So these leaks, they start small, they don't provide any negative pressure wave as such. I managed to find a picture of multiple, but they are together. In the case of spigot belt, for instance, you could have hundreds of those leaks around, and it will be important to locate them. And you are able to detect flow imbalances in your flow meter because you are losing quite a big amount of water in many locations. And the fiber optic is able to locate those several leaks at the same time that are leaking at the same time. So I don't think there is any other method can do that other than inspection, but not in real time. One of the biggest causes of water leaks is third-party interference, either by construction work or pipeline theft. There's been a lot of, I noticed you was mentioned before, there's a lot of pipeline theft in rural areas and communities as well. But on large pipelines, the main cause seems to be of real tragedies. In this case, somebody died here in this house, and this was a 3% leak, and it was caused by the dumping of all this rubble on top of the pipeline. And this could have been easily monitored by the fiber optic, and the company didn't know that this activity was going on there. So we are able to detect clandestine constructions like earthworks, landfills, mining, other competing infrastructures, gas, roadworks, and telecoms, etc. Actually, this gentleman here was stealing water, and sometimes it's near some constructions near the pipeline. In this case, pile hammer induced shock and vibration can shake the pipe to a point that cause a leak, and these constructions, they can be quite apart, but still able to damage the pipe. And fiber optic sensing can detect those works very well and protect your pipe for them. We in those cases before I was mentioned real-time monitoring, but we can also use insert the fiber optic inside the pipeline to monitor for retrofit or as inspection. So hydrophone inline inspection, as was shown here, is being used for a long time, and we can do a similar application. But the difference is you would leave the cable there for let's say overnight or a period of time, and the sound will then be integrated over time, and we'll be able to sense when there isn't less environmental noise at that location. In our case, you have to realize that it's not only the tip; it's the entire cable is the sensing element. Right? And these days, also fiber optic cables have been installed inside water pipes for telecom purpose in rural areas, especially. And if you can spare one fiber, this can be used for that purpose as well. In sewage pipelines, CPM, real-time transient models and other systems are very difficult or impossible because of first unmetered inlets. There is no flow meters at the inlets. It is a non-Newtonian fluid, very difficult to model. You can have again multiple simultaneous leaks and partially filled pipes. So there is no negative pressure wave. There is a very challenging situation for any leak detection system. But fortunately, sewage tend to be warmer than the ground, and we can detect leaks by monitoring the ground temperature around the pipeline, including very large diameters, even if they are not fully filled. I'm showing here another application, which is detecting storm water ingress in sewage systems. This was some trials done with our DTS in Japan. And to locate those stormwater ingress points is very difficult and very time consuming, and with a DTS cable, you are able to leave the cable there, wait for the next storm, and then you can see quickly where is the point where the water is cooling down. There is some overlap between these presentations and what was done before. I will jump this a little bit. We can detect manual digging with DAS, distributed acoustic sensing, machine digging, walking, fault like rupture, leakage, vehicles, and so on, which is very important for pipeline theft detection. Our system have a particular advantage over our competitors is that we use two polarizations, and you can see here the effect without polarization, the flickering at the top here, and the quality of the signal at 25 kilometers and the resolution that you get. And here with two polarizations, we are able to remove that effect of flickering here. And even at 50 kilometers, we have a very good results. So we have very good signal to noise ratio, even over a 70-kilometer range. DAS is a very transient event. No, it's an acoustic event. To classify those events is quite complicated, so we use machine learning to recognize the pattern and the type of activity that is going on. And so it's not only the equipment and the cable, but it's always also a very strong and complex software to make sense of that classification. We have classification tools to making rules and applying machine learning and changing the configurations. For pipeline leak detection, we have 4 modes to detect a leak. One is acoustic noise, orifice noise, similar to what was shown before. Distributed temperature grading sensing. So there is a variation in temperature that is captured by DAS. We apply also machine learning to these signals, and when there is a leak, the onset of a leak, a gasket breaks, or by corrosion, the thickness of the pipe is reduced to such a point that there is a sudden break of the pipe wall. A negative pressure wave can travel for hundreds of meters and many kilometers, and we can detect those, right? The advantage of monitoring negative pressure waves with fiber is that when you look at a negative pressure wave, it travels, you can detect those typically with pressure sensors. And between, let's say, 2 pressure sensors, you have a distance of minimum 10 meters. So you have a transient time between these 2 pressure blips of 10 milliseconds. Let's give an idea. I'm not even talking about what is the time that a pressure pulse passes on an individual pressure sensor. It's very, very fast event. But it's one pressure pulse that travels in both directions, and is being monitored by the fiber optic in the entirety of this progress. So we can track this negative pressure pulse for many kilometers over many seconds. And this is totally different from the situation that you have with a pressure sensor. So if the cable is close enough to sense the negative pressure wave, this is a very, very good system, and it can detect leaks similar to what can be detected by pressure sensors, if the negative pressure wave is there to be sensed, right? And also, you can have your pipeline damage, not necessarily have a leak, but you will be able to detect that when this pipeline was damaged, and go there and do a repair. For instance, to repair the coating so you don't have external corrosion, or some future pipeline rupture because of a crack that is opening, etc. I hope, can you hear this? No, you can't hear the sound, no?
No, we don't hear the sound. We only see the pictures moving.
Yeah, so you can see the digging, the digger digging a hole here, and the waterfall diagram here, and the system sensed and classified the event. In this case here, You have birds singing at the moment and a car passing near this road here. And the system is tracking, the cable is parallel to the road and is tracking the progress of the car. We do have a similar case in one of our projects, and is a road where nobody should be going there in the middle of the desert. So they want to know if anybody's near the pipe. We have many other presentations. I'm trying to compress this presentation a little bit. We have a software that makes sense of all of this and is available to view in different formats and in different locations, and give the information that the operator needs to take action, because a leak detection system cannot stop a leak. And what can stop a leak is the operator action. And if he has enough information, he will take action and send to the right location. Different third-party interference, or you call the police. If there is a big leak, you call, you take actions for shutting down the pipeline. We have asset formats and geographical displays, and you can see the different types of events and locations. You can zoom in and have more details about, for instance, in this case, temperature around the pipe. Again, it's a power cable, I think. We have many applications in all sorts of different fields. In pipelines, mostly is oil and gas, and but we do have a large trunk line, some final 250 kilometers in Saudi Arabia, and these systems are being specified in the Middle East now. So it's a fiber optic cable outside the pipe, and to detect and locate leaks, and also to provide third-party interference using the fiber optic, using DAS, distributed acoustic sensing. We have in Germany, I just wanted to show that a trench with a cable, and the cable is nearby, and you at the bottom of the cable, if there is a leak of hot water, hot liquid, you can detect by monitoring the environment, because it's a very similar application of switch, right? It will be exactly the same thing. You put the cable on the bottom of the trench, and we will be able to detect leaks this way. And thank you very much. And I will be able to explain in more details how can we help in the efforts for water leak detection pipelines.
Thank you, Dr. de Jode, for the presentation. You just made it on point. And also thank you to Mr. Clemens-Pohl and, of course, Mr. Edmund Riele. We have a few questions in the chat. So let me start with the first one. Is it possible to retrofit large pipelines with your technology?
We are discussing with some clients the use of cables inside the pipe. And obviously, I'm confident that we'll be able to detect leaks of sizes that would not be detectable using computational pipeline leak detection using flow meters. How small those leaks are, it will depend on the diameter of the pipe.
Thank you. We have another question. So first, words of thank you from this person. And so this person says that in some countries, it is not permitted to use technology. In Switzerland, for example. Do you know why? And another question is, what does it mean to have a low false alarm rate? How is it quantified?
I know that we looked at some, it's not only in Switzerland, but it was a question of certification of the cable to be used. And you have very strict regulations about inserting cables inside the drinking water, right? I have to say this is not the case in most places. And the use of fiber optic even to transmit internet in rural locations, now it's becoming common in New Zealand and some other places. And these cables are installed in quite small diameter pipelines, right? And so I don't think there is ground for this restriction. Possibly it's just a question of certification, regulation, and this will change like everything. I missed the second part of the question again, please.
The second part is, what does it mean to have a low false alarm rate, and how is it quantified?
We call false positives, and these are quantified in a number of events per month, and it will depend a lot as well on the magnitude of the leak you're trying to detect. If you try and how the system was built, right? So if you are having a system that is trying to detect leaks of 1%, it's the amount of on a large diameter pipeline, the amount of false alarms is going to be very, very limited. If you are trying to detect a very, very small leaks, seeping leaks, and then you may be able to accept a larger amount of false positives because there is no liability. You just send somebody there next week to see if there is a puddle there or not, right? Because if you have a very, very small leak rate, and if you send somebody down there after a few hours, right, you're not going to see anything. There is nothing there to be seen, right?
Thank you. Then we have a couple of questions here. The first is, so the person assumes that the technology can only be used if fiber is installed on the pipelines during new construction or rehabilitation, or is it also inside the pipe for longer times?
And typically, we're receiving now lots of inquiries from water pipeline consultants, and they are new pipelines. They are specifying DAS mainly, but also DAS and DTS, and the DTS at the bottom of the pipeline and the DAS attached or separated, the DAS on top of the pipeline, near the pipeline, and using the same cable for fiber optic for telecommunications. And we are receiving very little inquiries at the moment for retrofit. we are still probing the market and looking for partners and clients who have a pain, right? And one of the main things that are coming is the detection of rebar failure on concrete pipelines, pre-stressed concrete pipelines, and we are looking forward to start working on that. So the cable will be inside the pipeline and it will be left there for monitoring real time for long period of time.
Okay, we are already past our time, but I would like to address the questions already asked in the chat. So I hope you have a few more minutes. So I think you maybe address a little bit towards the cable. So can you do distributed acoustic sensing and distributed temperature sensing with the same fiber cable?
Correct, yeah.
Yes, okay. And then what is the estimated cost to install and operate the system for example, 10K transmission pipe?
It's a system that is it has its optimum values, right? So let's say if you ask me I'll give you a number and you divide by 10 kilometers to find the price for per kilometer. 10 kilometers is not a good value. We can do up to 70 kilometers with the unit that costs more or less the same price for a 10 kilometers. Sometimes what you have is multiple pipelines and they are in parallel or they are have a common place, and you can go and come back. And so what I'm trying to say is that if you have a reservoir and 3 or 4 pipelines coming out of this reservoir, you can put the unit there and you are able to detect leaks, in fact, cheaper than other methods, because you're doing multiple pipelines with the same unit. It depends, and it is competitive. When you talk about large diameter pipelines, computational pipeline monitoring is very expensive because of the flow meters there, and other methods can be and you don't provide such a good location, right? If you are also comparing the cost of leak detection, you perhaps not seeing the whole point, because most of our clients now are not the driver is not leak detection only, right? We are providing third-party interference. We are providing location of events, some that are avoiding a leak, right? And so it's difficult to give a price, and I'm afraid to mislead on a price here for 10 kilometers, right? And certainly a large diameter pipe warrants a good system to protect it. And catastrophic failure of these pipelines have been a big issue around the world.
Thank you. The 2 last questions from your the co-presenter as well. Mr. Edmund Riele, how often do you encounter cable faults and what is the cost per meter?
Cable faults are rare. What we have sometimes is a fiber fault, and you have spare fibers in the cable to compensate, give some redundancy for that. There are some redundant configurations is possible. You monitor the cable from both sides. So if there is a cable cut or a fiber cut, you are able to detect from both sides, right?
And then now I think the last question, Stefan, do you want to also give the closing words?
Thank you very much. Yeah, I'm in my interviews that I conducted with Mr. Pohl and Mr. De Jode, I stressed a lot the cost aspect, and I maybe could give a little bit resume what I found out. One thing is it is really a system that has a lot of economics of scale. So it's what Mr. De Jode already said. So actually the cable is cheap. Yeah, you have like, let's say 1,000 or 1.5 to 2,000 euros per kilometer, and the cable is already there. But the other aspect is very interesting. The prices for the analyzing devices are coming down very, very fast. So if you put the cable now and you wait 10 years and begin to measure, it will be much cheaper than before. And another aspect is, as I found out in interviews with other techniques like the smart ball or this Sahara system, is that the inspection, a one-time inspection of a large diameter system has almost the same cost that to monitor all the time with a fiber optic cable with, if you're using now, let's say, distributed thermal sensing. Distributed thermal sensing, DTS, is still a little bit cheaper than distributed acoustic sensing, but the problem is it cannot be used as often. Yeah, it depends on the difference between the water temperature and the surrounding soil. That's some of the ideas I've got, not only interviewing both of them, but also GTC Kappelmeier and seen other systems. So if you have a lot of large diameter pipelines, very long, and you use the same device and several, it can be sometimes cheaper to have a monitoring system than to make one or two inspections that could cost you, as a Sahara system, for instance, $7,000 a kilometer. Yeah, and it is one time. So I think it is a very, very interesting option, and it will be getting much more cheaper still in the future. It's a very new system, actually. Yeah, and I think it's a very interesting. Also, I made some calculations. I asked here in Peru what is an investment in a new pipeline, yeah? And let's say it is 1 to 2% of the investment is to install the monitoring system. Okay, that's what I wanted to add. Maybe already as a foregone conclusion.
Yeah, hello. Somebody have a very noisy.
Someone is vacuum cleaning in the background.
Okay.
It's a Dr.
Okay.
You raised your hand.
Yes.
To close the session as well. So.
Okay, I just wanted to say that you can install the cable and have it monitored as an inspection tool as well. So you can use the one unit and monitor all different pipelines. Provided the cable is there, you monitor for a period of time, and as an inspection tool, outside inspection tool. Okay, and thank you very much. I really appreciate for all these people and your time. And was great to hear the previous presenter as well. Thank you very much.
Thank you to all the presenters. Thank you.
Thank you very much.
Participants. It was a great, very informative, I think, for all of us. So I hope to see the participants again, and also hope to see the presenters again, of course. And well, take care of yourself and have a lovely day or afternoon or evening.
Thank you very much. Thanks for organizing, and bye for now.